back to another video. Today we'll be looking at stoichiometry, which is the third unit in the IGCSE 0620 chemistry syllabus. The first few topics for stoichiometry were actually touched upon by me in the previous video, but it doesn't hurt to go over it once again. So we'll start our day by learning about the concept of AR and MR. Now AR is relative atomic mass, that's AR. And as I mentioned in the previous video, it's the mass of an atom compared to the mass of 1/12 of a carbon atom. Not a carbon atom, 1/12 of it. Now what that means is that the best way to visualize it would be through a pie. So imagine this is a carbon atom and I have it divided into 12 parts. That's 12 parts. This is a carbon 6 atom, which is the most common isotope of carbon. And a carbon atom has a mass of 12. So 1/12 of a carbon atom, which is just one of these slices, has a mass of 1. So when I compare an atom such as Na, which is 1123, pretty sure, 1123, we can say that the AR of sodium is 11, and this tells us that the sodium atom is 11 times, the mass of a sodium atom is 23, which tells us that the sodium atom is 23 times heavier than 1/12 of the carbon atom, which has a mass of 1. And that's the concept behind AR, relative atomic mass. Again, just to reiterate, you're basically just comparing the mass of one whole atom to 1/12 of a carbon atom, not the entire carbon atom. And similarly, we also have MR, which uses the same concept. Now, MR can mean either relative molecular mass relating to molecules or relative formular mass relating to compounds. But the concept is the exact same. So for things like H2, O2, N2, diatoms basically, these guys have an MR of 2, 32, and 28 respectively. So a hydrogen molecule is 2 times heavier than 1/12 of a carbon atom. An oxygen molecule is 32 times heavier than 1/12 of a carbon atom, and a nitrogen molecule is 28 times heavier than 1/12 of a carbon atom, etc., etc. And this is applicable to diatoms, relative molecular mass. Let me write that down. Relative molecular mass. Right. There's also relative formula mass, which is also MR, and this has to do with compounds. Again, the concept is the same. Something like H2O, for example. Something like H2O has an MR of 18. So a molecule of water is 18 times heavier than 1/12 of a carbon atom. And a note that I want you guys to remember is that MR and AR don't have any units. So there are no units, because if you think about it, an AR or MR is just a comparison between two things. So you don't need a unit for that. And that's just something you need to remember for calculations and things like that. Now we'll be looking at the concept of the mole. Uh, the mole. I know most of you are thinking of the animal, but yeah, we'll be looking at the mole and Avogadro's constant. Let's write that down. Avogadro's constant. Pro tip, when I watch YouTube videos of people teaching, I like to watch the videos at 2 times speed. At least for me, that's like it's more efficient for me, like when it comes to absorbing knowledge. Yeah. So anyway, a mole is any quantity of a substance that contains 6.02 times 10 to the power 23 elementary particles. What that means is that 1 mole of, let's say, carbon, right? 1 mole of carbon contains 6.02 times 10 to the power 23 atoms. Now, in the case for carbon, 1 mole is the same as 12 grams. So 12 grams of carbon contains 6.02 times 10 to the power 23 atoms, which is why 12 grams of carbon is a mole of carbon. In the case for, again, sodium, let's say, Na, which is like this, over here, sodium, 23 grams of sodium, 23 grams of sodium is contains 6.02 times 10 to the power 23 sodium atoms, meaning that 23 grams of sodium is 1 mole of sodium. And that's the main concept behind what a mole is. And okay, I should mention this number is called Avogadro's constant. Basically, Avogadro was this guy that found that 12 grams of carbon contains 6.02 times 10 to the power 23 atoms. So from there, you can figure out that 1 mole of any he figured out that 1 mole of any substance will contain 6.02 times 10 to the power 23 atoms. And a mole is basically just the AR or MR of a substance expressed in grams. So yeah, that's more or less it. If you were to take the AR or MR of a substance and express it in grams, that's the molar mass. And the molar mass of a substance, for example, carbon is 12 grams, will contain 6.02 times 10 to the power 23 atoms. One important thing you need to know is the formula that relates all of these things together. So the number of moles, which is N, is equals to the mass of whatever you have. Let's say you have 50 grams of carbon over the AR or MR, depending on what substance you're dealing with. So since I take carbon as an example, you'll use AR. So N is equals to 50 grams, let's say 50 grams of carbon would be over 12. Would be over 12 because that's the AR of carbon, and that would give you 4.167 moles. The unit for moles is MOL, so you can just write mole. And that's just that's the very first formula in this unit. There are a lot more. So let's move on. Well, now we'll be looking at something called the empirical formula. That sounds kind of fancy. It really isn't. If anything, I would say that the empirical formula is like the poor man's formula. That's just something I like to call it. But empirical formulae basically show you the simplest ratio in which atoms exist in a compound. So for example, uh, uh, hydrogen peroxide is H2O2. Right. So hydrogen peroxide is H2O2. It exists in nature as H2O2. However, um, you can simplify this ratio as just HO. Now, hydrogen peroxide doesn't exist in nature as HO, but this is the simplest ratio that you can use to represent it. Another example would be propane, which exists in nature as C3H6. Propane is an alkane. It's an alkane with 3 carbon atoms. But the simplest ratio in which it exists is CH2. Sorry, it doesn't exist as CH2, but that's the simplest ratio that that shows the empirical formula. So in both of these cases, HO and CH2 are the empirical formulae for the above compounds. Again, that doesn't necessarily mean that the compounds exist in these ratios. It's just the simplest ratio in which a compound exists. It's the simplest ratio in which atoms can exist in a compound. Now, to find the empirical formula of a substance, you can't just like divide by 2 or like divide by the HCF. I'm assuming that's what most of you thought, but there is an actual process. But it's centered around the N equals M over AR formula from before. It's centered around this formula. So the best way to explain it is using an example. Right. So as you can see from this example question, a compound contains 0.12 grams of carbon and 0.02 grams of hydrogen. Find the empirical formula. So first, you start out by writing down the elements in this compound, that's carbon and hydrogen. The masses that have been mentioned are 0.12 grams and 0.02 grams respectively. The AR for both of these substances is 12 and 1. So you can calculate the number of moles by doing M over AR. If you were to plug that into your calculator, you would get 0.01 mole and 0.02 mole. And obviously, this is just, if you were to write this as a ratio, it would be 1:2. And yeah, that's just your formula. So your final answer would be C1H2. CH2. That's the empirical formula for this substance. Right. So here we have another example. A compound Y is 80% carbon and 20% hydrogen. Find the empirical formula. The first thing you'll notice here is that they haven't actually given you the mass or the masses for carbon and hydrogen. That's fine. Let's look at how you can solve a question like this. Again, you start by writing down the elements. Carbon is present. There's 80% carbon and 20% hydrogen. Now, in cases where they just give you a percentage, you can simply take the percentage as the mass. What I mean is, you can just take 80% as 80 grams and 20% as 20 grams. And now you just go about the process as usual. AR 12 1. Once you find the number of moles, which is 80 over 12, that gives you 6.67 mole. Over here you just have 20. Right, over here, to simplify this ratio, an easy method is to just divide both values by the smaller number. So you divide it as such. Divide this by 6.67 as well. Just a second. Right, sorry about that. So you divide both the numbers by the smaller value and you end up with 1 and 2.999, which you can just round up to 3. That's acceptable. So you end up with a ratio of 1:3, and you just apply that. So the empirical formula for compound Y is CH3. And with that, we are done with empirical formula. Now we come to the molecular formula. In some ways, this is just the opposite of the EF. So the molecular formula shows the actual ratio in which compounds exist, in which atoms exist in a compound, right? So H2O, this is the molecular formula for water. Atoms actually exist with this ratio. Another example is CO2. Atoms actually exist in this ratio for carbon dioxide. Right. So the molecular formula of, okay, let me write down this, actual ratio. So that's a keyword that you need to include in definitions. Usually, I don't think they usually ask for definitions. I might be wrong. Anyway, the molecular formula can be found using a formula. The molecular formula is equals to a factor times the empirical formula. I know that sounds confusing. Now the factor is equals to the MR over the EM. This is really confusing. I understand. This MF is the molecular formula, and this is the empirical formula. Now we all understand that if we were to multiply the empirical formula with a certain value, you would end up with the molecular formula. That's how the entire concept of simplification works. Now to find this factor, you basically take the MR of whatever compound you have and divide it by the empirical mass. EM stands for empirical mass. Let's just write that down. Empirical mass, which is just the mass of that substance if you were to use the empirical formula. The best way to explain this is using an example. Right. So over here we have another example, or we have our first example to demonstrate how to find the molecular formula. A molecular compound has the empirical formula of HO, and its relative molecular mass, which is its MR, is 34. So you find the MF. Recall that, I would like you to recall that the MF is equals to a factor times the EF. Now the main thing, you've been given the EF, which is HO, but you don't know the factor. So the factor, again, is the MR, which is 34, over the EM. Now the EM hasn't been explicitly stated, but because you know the empirical formula, you can calculate it. So to find the EM, finding the EM, what you do is that you take the empirical formula, and this is just 1 plus 16, where 1 is the AR for hydrogen and 16 is the AR for oxygen. So the empirical mass is 17. That's the EM. So the factor is 34 over 17, which is 2. So you can find, so your factor 2 can be applied to HO, and this will give you an empirical formula, a molecular formula of H2O2. And that's how you find the molecular formula of any compound. Well, now we are going to be looking at the percentage composition, which basically just tells you how much of an element is present in a compound as a percentage. So the quantity of an element in a compound expressed as a percentage. Again, let's take an example. Let's say the question goes something like, calculate the percentage composition of sodium in sodium oxide, for instance. So sodium oxide is Na2O, and to find the percentage composition, you would take sodium over sodium oxide times 100%. If you were to put this as chemicals, as the symbols, it would be 2Na. Notice the 2, right? Because in the original formula, 2 sodium atoms combined with 1 oxygen atom to form sodium oxide, basically. So 2Na over Na2O is times 100%. And now you basically just use the AR and MR for each of these substances. So 2 times 23, which is the AR for sodium, is 46. And the MR for sodium oxide is 62. Times 100%, you just plug it into your calculator and you end up with a percentage composition of 74.2%. Now what this tells you is that sodium oxide is 74.2% sodium, and let's check my math skills. It's 74.2% sodium and 25.8% oxygen, I think, pretty sure. Yeah, that's this percentage composition. Okay, quick note, a lot of questions, rather than just asking you directly to find the percentage composition, they might say something like, find the percentage by mass of X in Y. Over here, you do the exact same thing. They're just asking you to find the percentage composition, but they're trying to trick you. So percentage by mass is the same as finding percentage composition. And yeah, that's about it for percentage composition. Right. So now we come on to mass-mole relationships, which is simultaneously one of the easiest yet most arduous processes or like topics under stoichiometry. And really the only way to really explain it is through an example, and it's just up to you to practice it a lot. So let me take the example of a reaction between hydrogen and oxygen to form water. As you can see, a balanced equation, and what this equation, you can determine a few things from this equation. Number one, you can determine the mole relationship. What I mean by the mole ratio, mole ratio. What I mean by mole ratio is you can look at the coefficient, and the coefficient here is 1, but you obviously don't need to write 1 because that's not necessary. And the coefficients tell you how many moles of each substance there are. So you can see that 2 moles of hydrogen reacts with 1 mole of oxygen to form 2 moles of water. Let's write that properly. 2 moles of water. So that's the mole relationship in this reaction. You can also get the mass ratio. You can calculate the mass of each of these substances by multiplying the coefficients and the subscripts with the AR or MR of each substance. So what I mean by that is H2 is 2 grams, right? So, but the coefficient is 2. So 2 times 2, that's 4 grams. O2 is 16 grams, or 1 mole of oxygen rather is 16 grams. and 2 moles of water is 36 grams. Now, I'm so sorry. Uh, 2 moles, 1 mole of oxygen is 32 grams. Yeah, 32 grams. There are two things that I want to point out here. Number one, 4 plus 32 is 36. That tells us that confirms the law of conservation of mass, where mass is neither created nor destroyed, and it only changes from one form to another. No, it's not created or destroyed. That's what I'm saying. So, and secondly, if you're ever unsure about your relationships, you can usually, at least for the mass ratio, you can double check by making sure that the masses in the reactants add up to whatever is there in your product side. Right. Now it comes to actually using this in a practical manner. Right. So here we have a sample question. It's just like a question that I made up. A. Using the reaction on the left, determine how many moles of oxygen is needed to react with 10 moles of hydrogen to form water, where mass is required. The main thing that you should do when you come across questions like this, number one, you need to identify the elements that they're talking about. They're asking you to find you need to find the moles of oxygen. That means your oxygen is like it's your unknown value in a sense that react with 10 moles of hydrogen. So hydrogen is the known value. So you use oxygen and hydrogen for A, where I have 2H2 and O2, and they're talking about moles, and the way the question has been phrased, I can directly use the mole relationship. So 2 is to 1, and now they're just asking me, they mentioned that there are 10 moles of hydrogen, so 10 moles of hydrogen, and your oxygen was the unknown value. Let's double check. Yes, it was. So you can just cross multiply, and your x is equals to n times 1 over 2, which is just 5. And an important thing in stoichiometry, never forget your units. So 10 moles, 5 moles. What this means is that when 10 moles of hydrogen, it means that 10 moles of hydrogen will react with 5 moles of oxygen to maintain the reaction above, in a sense. If that makes sense. I could have phrased that better. Now let's tackle B. Again, you need to identify the elements that they are the elements or compounds that they are talking about. So what mass of water is formed? So that means water is your unknown value if 2.5 grams of oxygen is used. So oxygen is your known value. And the way the question has been phrased, you can directly use the mass relationship. So I have 2H2O and O2. This is 36 grams as per my mass ratio. This is 32 grams. That's the ratio. They mentioned that 2.5 grams of oxygen is used. So let's write that down. That means this is our unknown value. So to find x again, you just do 2.5, you just cross multiply. So you have 2.5 times 36 over 32. X is equals to, you can just plug it all into your calculator, and the value is 2.81. Again, never forget your units. They were talking about mass before, and all of the units in your working out, while you were working it out, all of your units were grams. So this will also be in grams. And with that, we have tackled mass and mole relationships. Of course, there are many types of questions out there, and some of them even combine mass and mole relationships. We might look at that later on. But the main thing I want to do now is touch on the limiting agent and the excessive agent, or the thing that is in excess. Now, what do I mean by that? Let's see. Right. So now we come to the topic of limiting agents and reactants that are in excess. I have a reaction over here between magnesium and chlorine to form magnesium chloride, yeah. I've already written down the mole and mass relationships, and the question that I came up with, if 20 grams of magnesium and 70 grams of chlorine were used in this reaction, which of these reactants would be the limiting agent? Now, the limiting agent is the reactant that is in short supply. It's going to be easier to understand once I explain it. So what you have to do here is that the reactants you're looking at the reactants. So you take magnesium and chlorine, and because the question uses mass, the question mentions mass, so you look at the mass relationship. Magnesium is 24 grams, chlorine is 71 grams. That's the mass ratio. And they mentioned that 20 grams of magnesium was used with 70 grams of chlorine. So let's just take 20 grams here and check how much chlorine would needed to react with it to give a perfect amount of magnesium chloride. So once you do all your calculations, you'll see that X is 59.17 grams. This means that 20 grams of magnesium will perfectly and completely react with 59.17 grams of chlorine to form whatever mass of magnesium chloride. However, they mentioned that 70 grams of chlorine was used instead. That means they're using more chlorine than you actually need, at least in theory. And that implies that chlorine, at least in this scenario, is excess in supply. So that's an excess. And by proxy, magnesium is the limiting agent. Because if you had more magnesium, all of the chlorine would be able to react. But because magnesium is short in supply, it's limiting how much chlorine is able to react to form magnesium chloride. Right. So with that, we are done with limiting agents and also reactants that are in excess supply. And now we come on to the last two topics that fall under stoichiometry. The first one of them being the molar volume of a gas. Now, the molar volume of a gas is just the volume occupied by 1 mole of a gas. So if I have 1 mole of a gas at room temperature, so at RTP, room temperature and pressure, or STP, standard temperature or pressure, they mean the same thing. So the molar volume of a gas is the volume occupied by 1 mole of a gas at RTP, 1 mole of a gas at room temperature and pressure, or standard temperature and pressure. And this is, of course, as I mentioned in a previous video, 20 degrees Celsius and 1 atm. So now what does this mean? It means that at 20 degrees Celsius and at a pressure of 1 atm, if I take hydrogen, for example, 1 mole of hydrogen, if I take hydrogen as an example, 1 mole of hydrogen is 2 grams. And at RTP, this 2 grams of hydrogen will occupy a volume of 24 dm cube. Yes, not 24 cm cube, 24 dm cube, decimeter cube. Let's take another gas, oxygen. 1 mole of oxygen is 32 grams. So at room temperature and pressure, 32 grams of oxygen will occupy 24 dm cube. Let's take another gas. Nitrogen. 1 mole of nitrogen is 28 grams. So at room temperature and pressure, this 28 grams of nitrogen occupies 24 dm cube. Right. And that's really what the molar volume of a gas states. Basically, under standard temperature and pressure, 1 mole of any gas occupies 24 dm cube. Keep in mind, 1 dm cube is 1000 cm cube. 1 dm cube is 1000 cm cube. So 24 dm cube is 24,000 cm cube. And 1000 cm cube is 1000 milliliters, and 1000 milliliters is 1 liter. This will be important once we look at solutions and concentrations. And that's about it for the molar volume of a gas. And now we come on to concentrations and solutions. I lied. We still have one more thing for molar volume of a gas, and that's the formula. So basically, V is equals to N times 24. Basically, if you want to find the volume of a gas at STP or NTP, you can take the moles. So, let's say I have 36 grams of oxygen. I can calculate how many moles that is using N equals M over MR, and then I can just multiply by 24 to get the volume at STP or RTP. And yes, now we're finally done with the molar volume of a gas. And I lied again. We still have percentage purity and percentage yield left. So let's tackle that. Right. So let's start with percentage yield. Percentage yield is essentially just, so as I was saying, the percentage yield is the amount of a product that you obtain from a reaction expressed as a percentage. Now, in theoretical terms, the percentage yield for any reaction could be 100%, but practically speaking, that's usually not the case. Now, the reason percentage yield is never 100% isn't because mass is lost. Mass is not always conserved. However, percentage yield is usually lower than 100% due to impurities in the reactants, or due to energy losses, or even due to human error. So that plays a part. You can calculate percentage yield as the theoretical mass, which is the mass that theoretically you could obtain, which you find via calculate. Oh, I made a mistake. Percentage yield is the actual mass, the actual or experimental mass, which is the mass of the product that occurs in practicality or during an experiment. So the actual mass over the theoretical mass, which is what you calculate using mass and mole relationship. So theoretical mass times 100%. And the percentage, this is yield. And percentage purity is just it's really, well, in a way it's just, I'm sorry. So percentage purity is the quantity of a substance that is pure without any impurities in it. So percentage purity expressed as a percentage. So percentage purity is a pure substance So this could be the mass of the pure substance, it could be the volume, etc. The main thing is that the units for both your numerator and denominator should be the same. So pure substance over impure substance, substance times 100%. That's percentage purity. Now, one thing about impurities is that impurities can lower the melting points of a substance and increase the boiling points of the substance, and they can also you can measure the degree of impurity based on the change. So the greater the change in the melting and boiling points, the more impure your substance is. And that's all you need to know about the percentage purity and percentage yield. Now, finally, we can move on to concentrations and solutions. Right. So the concentration of a solution is the amount of solute that is dissolved in 1 dm cube of a solvent to form a solution. Now what this means is that if I have, the units for concentration could be grams per centimeter cube or moles per centimeter cube, but in chemistry, more often than not, dm cube. Moles per dm cube is preferred. So what this means is that 1 mole per dm cube, let's say this is a solution of sodium chloride in water. What this means is that 1 mole of NaCl was dissolved in 1 dm cube of water. Now, an important thing to note here is that I don't necessarily need to use 1 dm cube. If I were to dissolve 1 mole of NaCl in, let's say, 50 centimeter cubes of water, which is still a lot, I could still express the concentration as moles per dm cube. Before that, I should mention the formula. So concentration is equals to the mass of the not the mass, sorry, the amount of solute. I think that's a good way of phrasing it. Amount of solute, which is expressed in moles, over the volume of the solvent, which is expressed in dm cube. Now, as I was saying, I don't have to use 1 liter of water just to make a solution in a lab. I can use, let's say, 5 centimeter cubes, but I can still express the concentration in dm cube by simply converting 5 centimeters to dm cube before plugging it into this formula and calculating the concentration. And in fact, you can kind of simplify it as C equals N over V. So concentration equals number of moles over volume of solute. And that's about it. One thing, 1 mole per dm cube may also be written as 1 m, 1 capital M. It means the same thing. And of course, you can also rearrange this formula as N equals CV, which is another way of finding the number of moles. And yeah, that's about it for concentrations. You should also know about titration, but that comes in towards the very end of the syllabus, around chapter 12. So maybe like put a pointer on your calendars for that. Right, and with that, we come to the end of another chemistry unit. And stoichiometry is over. I know stoichiometry is a headache for a lot of students, but I feel like if you put enough time into practice, it is doable. And this is also, like, as of now, it's the shortest video on this channel. So that, well, do with that what you will. Yeah, so thanks for watching. Maybe consider subscribing, I don't know. And see you next time.